Hello, I'm going to make a quick video tutorial on how to solve problem 8 from problem set number 2. And in that problem, what you need to do is a computation for two gases, the gases that you select for your problem set, and calculate the interaction energy for those two gases. Right? So it's just very simple. Here, create a new job, and then you're going to select your two gases. For example, I'm going to select neon. It's one of my gases. And the other, I'm just going to use a diatomic molecule, HF. And then hydrogen is here. And the reason I put them in this way is because I know fluor is very electronegative and hydrogen is less electronegative compared to fluor. And the electron density is going to shift to fluor, so this is going to be partially positive. So it would like to interact with the electron density of the neon. And what I'm going to do also is kind of a type of hydrogen bond right there. So distance between the two, and then just ready to do just the computation. So that's the first thing you have to do. So press here, class long. Already have the name. Instead of molecular energy, just do geometry optimization. I'm going to use a small basis set. STO3G is the smallest possible basis set you can use. So I wanted this to be a little quick. And submit. And it's running already. Okay, it should finish pretty quick. I hope. It's complete. Okay, so once it's finished, you open it. Okay, that's the interaction. That's the type of interaction I got from this optimization. And then you go here, restricted Hartree-Fock energy. So you want to copy that energy. Control C, copy, and then I'm going to paste that in, I don't know, Excel. Okay, for now. And I will share with you this a little bit later. Okay, once we do that, we now want to do two more computations, one for each one of these. So new job using this geometry. So I'm going to delete that neon. I'm just going to do a computation for HF on HF, Hartree-Fock, STO. It gotta be exactly with the same level of theory. Gotta be Hartree-Fock and exactly the same basis set. Otherwise, it won't work. You're gonna have a very strange numbers for the interaction energy. Okay, so it's complete. It's done. It's run pretty quick, and we're now gonna go and copy that energy. Okay, I'm gonna go here. It's 98. Something hard trace, don't copy the hard trace. I'm just gonna go here, I have an Excel sheet open, the value, and then gonna label this HF. Okay, and now the last computation that I have to do is for neon. So for that, I want to go back and I want a new job. Okay, new job. Or I could just delete that one and do it there, which usually is the best way to do it. Let me show you why. Let me go back and let me show you why it's the best way to do it that way. So I open HF or the other one, whichever I want. Okay, new job using this geometry. In reality, I'm not going to use that geometry. I'm just going to get the neon here, and then I'm just going to delete everything else. And the reason, oops. Here. The reason I want to do this is because now when I go to compute, the level of theory is already set. You see HF, STO3G. Now it's a geometry optimization. This is actually an atom. You don't have to do geometry optimization for an atom. If you do geometry optimization, nothing's going to happen. It's going to work anyway. But it's just to be just energy. Okay? Because there's nothing to optimize in an atom. Right? So you submit that. And is running. Running is complete. Now I open this and I copy the energy. Using countries. I'm gonna put it in the Excel sheet I have here, which I'm gonna be sharing with you soon. Okay. Perfect. Let me now go here. I'm gonna stop sharing the screen for the computation, and So what we have here now is the energies that we copy from our computations into Excel. So the energy for the interaction neon HF, that's the total energy for that system, and that energy is in Hartrees. The energy for HF molecule is here, and the energy for the neon is also here. So how we calculate the interaction energy? So that interaction energy, we expect when those two molecules interact, okay, that molecule and that atom actually, the energy goes down, okay? So that's why the energy is going to be negative, okay? So how you do this? Well, you're going to take the energy for the neon HF interaction and you're going to subtract that to the addition of the energy of HF and the energy of neon. And that's going to give you this value. It's a really, it looks like a really small value because the energy is in Hartrees. You take that value and you multiply by 2625.5, and that's going to give you minus 6.38 kilojoules per mole. That's how you change to kilojoules per mole. So that interaction energy is minus 6 kilojoules per mole. Okay, and the opposite sign of that is DE, the dissociation energy. Okay, if you want to dissociate that interaction, that will be DE, which is positive. So it will be positive 6.38. So this is another way to calculate that energy for the interaction. Okay, now what I'm going to do is explain problem 9 from the problem set. Will be the next one. And problem number 9, what you have to do actually is then let me share here, is just to do a computation for the electron density, right? MO. So here HF neon. If I go to HF neon now, what I need to do is just to calculate now, and this is for the next problem, do a computation here for the molecular orbitals. So here I do molecular orbitals, do the computation. I like to do everything the same level theory. And it's complete. One thing, couple of things from here. First, you will see if you do electrostatic potential energy here, you will see what I was telling you. You see this area is blue, okay, and this is red, more negative. So it's because this is very positive here, right? But that's not what we want. What we want is these. These are the molecular orbitals. Okay, this is the HOMO, the highest occupied molecular orbital. So you can actually take these energies for each one of those orbitals, right? However far you want to go. Of course, you're not going to do the core. It will be almost impossible to do the core for that molecule. Not for this one, actually. Just do it for one molecule, because you're not going to be able to do the. You're not going to be able to do the. I did the wrong one. Good job using this geometry. You're not going to be able to do the photoelectron spectra for that interaction, if possible. So you got to do it for a molecule or for an atom. So molecular orbital here. So refresh very quick. It's done. So what you will see here is a couple of things. So these are the molecular orbital for that molecule HF. So this is the highest occupied molecular orbital. So these are the energy of those orbitals. So you can now predict the photoelectron spectra. For that problem, I want you to draw the photoelectron spectra using those energies. You see what you predict for those energies. And then you can tell me what type of orbital. For example, this one, I will look. This is this. It's kind of a lump here, actually. Okay, so you have that one. Then you have this one. Will be the other one. Actually, they're similar. So these are degenerate. Okay, so keep that in mind when you're doing this. These are the other molecular orbital. Look at how pretty. Look at this one. Okay, so these are all the molecular orbitals. This is a core orbital. I mean, to take out those electrons from this atom, you will have to break it. Have to break this molecule. Okay, so using this, you can plot the photoelectron spectra that you will predict for HF. Okay, and that's what I want. If we go also down here, You see electrostatic potential? If you click in there, it's going to show you what I just told you before. The blue one is positive and the red one is negative. So that's why this part wants to interact with that neon. Okay, so I will leave you to here with the tutorial. Okay.